Okay, so then it's time to start the first talk of the day. I'm happy to introduce Jeff Harvey from University of Chicago, who will give a Blackboard talk. This is the first Blackboard talk of the conference. This will be about superconformal symmetry and quantum error correction. So please, Jeff, go ahead.
Okay, thank you very much. So I'd like to thank the organizers for the invitation to speak here. I'm going to be talking about some work that I did with Greg Moore in this paper, now published in JHEP. And unlike some of the speakers the other day, I don't have small children running around, I don't have cicadas in the background, but I do have to teach a large number of undergraduates about the fine and hyperfine structure of hydrogen a little bit later today. So I'm not going to be in the discussion section at the start, but I can be there for about the last 15 or 20 minutes, depending on how quickly I can get rid of my undergraduates. So if you have questions that aren't answered during the talk, feel free to ask questions. I will be available in the discussion section then. And of course, you can ask Greg since he was my collaborator. So this paper was inspired by a couple of things. One was Matthew Moonshine, discovered now 11 years ago by Eguchi, Oguri, and Tachikawa that there is some sign of the Matthew group M24 in the elliptic genus of K3 surfaces. And it's kind of embarrassing that we still don't really understand why. And so we wanted to understand this. And then we were very directly motivated by a really nice paper by Gabardine, Taormina, Volpato, and Wendland, who looked at a particular superconformal field theory that corresponds to a K3 sigma model and that has a very large symmetry group that preserves the 4,4 superconformal symmetry. And in this paper, they said things like the basis of Ramon states corresponds to something called the miracle octet generator, which is a device, mathematical device that's used to construct the Golay code. And so we wanted to know, what is the MOG doing in K3? And more generally, I'll say a little bit about what the MOG is, but it's a way of constructing the Golay code. And the automorphism group of the Golay code is M24. So although in their paper, they identified certain subgroups of M24 as preserving the superconformal symmetry and used that to establish this group, we were hoping that maybe if we could understand at a deeper level what was going on here, that we would get an important clue of how to find M24. So we didn't succeed in doing that, but we did find some other things which I think are interesting, which I'm going to try to explain to you, although I'm not going to explain everything in our paper because there's a lot of technical detail. So I wanted to say before explaining some of the detail that moonshine, which is really the topic here, includes both general principles and very specific models. So I would say the general organizing principle that has been most useful is the role played by genus 0 subgroups of SL2R. These, in monstrous moonshine, organize the Mackay-Thompson series, which are kind of character-valued versions of the partition function. They classify the various kinds of umbral moonshine, as was shown in a paper by Cheng and Duncan. And they also, in some work that will hopefully appear one of these days with that I'm doing with John Duncan and Brandon Rehun, they also classify another set of moonshines, of which moonshine for the Thompson group is one example. So there's some general organizing principles, but of course, there's also a great deal of work that has to do with very specific detailed models. And here the sort of ultimate example is the two-dimensional conformal field theory or holomorphic vertex operator V natural constructed by Frenkel, Lepowski, and Merman, which is the space in which monstrous moonshine lives and acts. So this particular K3 superconformal field theory, which was not first written down by these people, but since they did such a nice job of studying it, I'll refer to it as the GTVW K3, is, well, it doesn't explain M24, but it's somehow like this V natural of FLM, in that it's a very detailed, rich structure with a large symmetry group and a very intricate structure. And we've uncovered some new features of the intricate structure in that model. So the general lesson that that we will try to extract from this is that there is a new connection in this model and in others between the construction of superconformal symmetry and quantum error correction. I should say for the kind of VOA people in the audience, if there are some, that of course, classical error correction plays a very important role in many constructions in vertex operator algebras, and plays a very, for example, an important role in constructing special lattices, which play a role in lattice VOAs. But I think the appearance of quantum error correction in conformal field theory is a new aspect. So lecturing at the blackboard has the advantage that I can't go too fast. It has the disadvantage that I can't cover very much. And I'm a little afraid that I might run out of time, but we'll see how it goes. Okay, so my plan is to quickly say a little bit about some of the codes and error correction that appear in this particular conformal field theory. So I'm going to start by talking a little bit about classical error correction. Which will allow me to introduce some of the ingredients. I'll then move on to talk about quantum error correction very briefly, and then I'll try to show you how some of the structures that I've discussed in talking about error correction are manifested in this particular theory. So in classical error correction, one usually starts with some prime power and the field FQ associated to that prime power. And then you imagine a message which consists of elements of that field. So we might have some long message with each one of these elements being in the field. And if we have a long message, it's often convenient to break that up into words. So we'll imagine that we have words of length K, which I have broken this message up into. And what we want to do is we want to encode this into a bigger space in a way that will allow us to detect and correct errors. So what we're going to do is we're going to encode this in a set of words with n greater than k. And in the particular case that we're going to be looking at, we are going to be considering linear codes. So for a linear code, there is a code word which is in FQ to the n, and that code word is our message word times a n by k matrix G. So this is our message, and we encode it linearly in a bigger space. And this matrix G can be written in a canonical form as just an identity matrix and then another matrix. So essentially the first k digits of G are the message, and then they get encoded in some way. We'll refer to this as an NK code and sometimes as an NK code, where D is known as the Hamming distance, and it's the minimum over all words in the code subspace, which is the subspace spanned by all the code words, of the distance between two code words. And this distance is the number of digits where C1 and C2 differ. So to save time, I have written down a few details of some examples here. So in particular, up here, I have written the generating matrix of the 743 Hamming code. So this takes this is a code where Q is equal to 2. We're working over a field with 2 elements. We have 4-bit words that we encode into 7-bit code words. And the feature that is important about this code is that the Hamming distance is 3. And this 3 implies that if you have a 1-bit error, that gives you a word with distance 1 from a code word, since you've just changed 1 bit. But because the next code word has distance 3 from the word that you started with, there is always a unique code word that is closest to the word with 1 error in it. So that allows you to correct any 1-bit error by simply finding the closest code word to the word with the error in it. Now, I mention the Hamming code because it's related to 2 other codes that play an important role in CFTs and in this model. So first of all, there is an 8-4, I guess, binary Hamming code, or extended Hamming code, that you get by adding a parity bit. And there's a well-known relationship between this extension of the Hamming code and the E8 lattice, where the Hamming distance of the code translates into the sphere packing properties of the E8 lattice. And there's also another code called a 6-4 code, where you drop the 7th digit. And this code is going to reappear in this K3 signal model. And I've written down the 16 code words in that in a notation to the left there, where we list the entries with a 1. So for example, this entry here with 235 means it's 0, 1, 1, 0, 1, 0. There's also a code which is going to play a role here called the hexacode. And the hexacode involves a field over a field of order of characteristic 2 and order 4, which is something that physicists don't usually encounter. Physicists, I think, tend to think that all fields are ZP with P a prime, but okay, they're not. And the hexacode is based on the field F4 with 4 elements here, and has a generating matrix, which I've listed here. And here I've written down the addition and multiplication rules if you want. They're also in our paper, but just as a reference. Why is the hexacode important? Well, for us, it's important because it plays a crucial role in a construction of a larger code called the Golay code. And that appears in this particular K3 sigma model. So I think it's difficult to give all the details, but I'll just say that there is an extended binary Golay code which takes 12-bit words, embeds them in 24-bit code words, and can correct any 3-bit errors. It was also used in various missions like the Voyager 1 and 2 missions to transfer data. The MOG is a way of constructing this code subspace. So this is there's a code subspace, which is a 2 to the 12th dimensional subspace of F2 to the 24. And you can actually construct it by hand using the MOG, which is kind of an astounding fact. And the book, the Sphere Packings, Lattices, and Groups book, gives you practice in doing this with some exercises. But the basic element of the MOG is that you take an element of F4 and an element of F2, a plus or minus if you want, and then you construct certain maps which take an element of F4 and F2 and produce an element in F2 to the 4th. And then there's an extension of this, which takes 6 copies of this into F2 to the 24th. And if you think of an element here as a list of elements in F4 and F2, then whenever X1 to X6 are in the hexacode, which is the code defined up here by this matrix G, and whenever the sum of the epsilons is 0 mod 1 mod 2, then this is in the Golay code. Or rather, it's in the even Golay code. And then there's a version of this that involves G minus and F minus, which adds the odd elements. So I'm not going through the details, obviously, but this little picture over here kind of gives you an example. It takes an element of the hexacode And then according to these plus or minus signs, you associate to that elements of f2 to the fourth, and then you do that 6 times, and you get a 6x4 array of zeros and ones, and this encoding tells you that this will be an element of the Golay code. And the hexacode is small enough and simple enough that you can learn to recognize its code words kind of by hand, by looking at them. And then this encoding tells you how to construct all elements of the Golay code. Okay, so that's my extremely quick review of classical error correction and certain error correcting codes that are going to reappear in the context of a K3 sigma model. So my next task is to say a few words about quantum error correction. And in quantum error correction, we typically deal with Q bits, although we could deal with Q trits or higher, versions of Q bits. But for our purposes, a Q bit is simply a state in a two-dimensional complex vector space. So I'm using 0 and 1 as an orthonormal basis of our complex vector space. And in quantum mechanics, you either normalize your states or the overall norm doesn't matter. So strictly speaking, if we think of this state psi of this form, then psi is really an element of CP1. Now, in trying to formulate quantum computation, you have the problem that there's all sorts of noise, and it's very hard to maintain quantum coherence in quantum mechanical states. So the environment, cosmic rays, whatever, can sometimes act on these bits, either to flip them or maybe change their phase, or in general, do some kind of unitary transformation that destroys the information. And we're used to the idea in quantum mechanics that if you try to measure an observable, that you destroy information. So for example, you might try to measure the observable, which is the projection operator onto the state 0. And of course, if you get 0 for this measurement, then you know you're in the state 1. And if you get 1, then you know you're in the state 0. And after the measurement, this is the state or this is the state. And the information in A and B, which is picking out a point in the block sphere, is destroyed by the measurement. So it seems difficult, but you can use entanglement to solve the problem of how you can encode quantum information in a way that you can detect and correct errors. And I think the simplest example of this is to take this 1 qubit state and embed it into a state with 3 qubits, so in the tensor product of C2 with itself 3 times. And now, if you have a 1 qubit flip error, let's say, just for example, so a bit flip error is an error that takes a single 0 to a 1 or a single 1 to a 0. If that happens to this state, you can make a measurement to figure out what happened, and then you can do a unitary transformation to restore the information in the original state. And the way you do this is you measure a set of commuting operators. So there's a projection operator, and if you get 1 for this projection operator, then you know that there was no error. Then there's another projection operator, and if you measure one for this projection operator, then you know that the error was in the first bit. And similarly, there's one for the second bit and one for the third bit, where the second entry or the third entry is this distinguished element of this list. So these are 4 commuting projection operators. They can be measured simultaneously, and their eigenvalues tell you where the error occurred. And once you know where the error occurred is, then there's clearly a unitary transformation that just flips that bit back. So particular kinds of errors, bit flip errors that just change a 0 to a 1 or vice versa, can be detected and corrected in this way. And the basic idea is that you have this 8-dimensional space, and you have arranged things so that when there is just one error, it takes the state into an orthogonal space, and there are projection operators onto orthogonal subspaces that can measure where that state that's orthogonal to the state you started with is. And that's possible because you're now working in a higher dimensional space. So this is an example of how you correct a particular quantum error, but there are other kinds of quantum errors that you can consider, and you want in general to be able to detect and correct those if you're going to implement quantum computation. So my general understanding of the state of quantum computation right now is that while you can build quantum computers with increasing number of qubits, really effective quantum computation is going to require error correction. And so orders of magnitude more qubits than are currently used in order to actually implement this error correction. So there's a general formulation of what quantum error correction is that you can find discussed in John Preskel's notes or the book by Nielsen and Chang or in other places. So if we have the Hilbert space of n qubits, a quantum error correcting code is a Hilbert subspace C along with a set E of error operators that catalog the kinds of errors that you want to try to correct, and that satisfy that if EI and EJ are in the set E, then if P is the projection operator onto C, this code subspace, and EI and EJ are error operators, that there is a Hermitian matrix, alpha ij, such that the errors obey this. So this is kind of related to projecting onto the subspace, acting with an error, and then taking the inner product of that and showing that it, up to this Hermitian matrix, projects onto the subspace. Now, I'm not going to go through the details of how you detect or correct the errors given this condition, but it's explained in the references that I gave you. For us, the possible errors are going to be tensor products of what are known as Pauli operators in the quantum computation world. That is, they're going to be combinations of xy, zi acting on the ith component of our tensor product space, where these are just the usual Pauli matrices. but now written with capital letters because that's the notation that the quantum computation people like. So for example, on, I don't know, C2 to the fifth, we might have something like XY, the identity ZX. That would be an example of a possible error operator that could act on states in this space. And there is also a notion here. So when we have C2 to the N, and when our code subspace has dimension 2 to the K, where K is clearly less than N, then we call this an NK code, but we put it in double square brackets in order to indicate that it is a quantum code rather than a classical code. So there's one more notion that we need, and that is an analog of the Hamming distance for quantum error correction. The Hamming distance for classical codes tells you how many errors you can detect and correct, and there's an analog of that for quantum error correction. Namely, D is defined to be the minimum weight of the error operators in your set of error operators for those operators that are not the identity on your code subspace, and where the weight of E is the number of slots that don't have the identity operator, that have an X, Y, or Z. So I'm going to be talking about, specific things here, and the specific thing here is a code that is a 513 code. So that means the code subspace C is a one-dimensional subspace of, or well, two complex dimensional subspace of C2 to the fifth. So this code is the smallest code that corrects any one qubit Pauli error. And there are various ways of constructing these quantum error corrected codes. This particular one is constructed as a stabilizer code. So for this code, the code subspace is the subspace stabilized by a group S, and the group S can be defined by its generators, which are a set of unitary operators. So I'm not writing down these because I don't think you possibly remember them, and the details don't matter so much. But there is a particular two complex dimensional subspace, which is stabilized by these, and its elements can be written as a sum over group elements of the group element acting on the state 0 to the sixth, and then there's a rather simple operator acting on 0 bar. So these two states are a basis of the code subspace. And with some work, you can show that what I claimed is true, that there are a set of measurements of projection operators that you can make that will allow you to detect and then correct any error induced by the action of X, Y, or Z in any one of the slots of the bit. And then finally, there is one kind of not quantum error correcting, but nonetheless interesting state that you can make by adding one more auxiliary state. And that is in C2 to the sixth, you can create a state which just takes your auxiliary bit and entangles it, if you want, with the state in this code. Now, this state is a rather special state, and I learned of one of its special properties in the notes by John Preskill. It's a kind of higher dimensional version of the maximally entangled states that play a role in, Bell's theorem and the EPR paradox, in that if you take the density matrix, which you get by tracing over any 3 of the 6 qubits, so tracing over half of the qubits, you get a totally random state that is proportional to the identity matrix. This is an extremely non-trivial fact and shows that this state is special and somehow a kind of higher dimensional version of a maximally entangled state. Okay, so I've used more than half of my time, and I haven't said anything about physics or K3, but I've talked about some weird math. Well, excuse the weird, but anyway, some math involving the MOG construction of the GOLE code and some very special quantum error correction, which is special in the sense that it's the smallest code that allows you to detect and correct one quantum error, just like the Hamming code up here is the smallest classical code that allows you to detect and correct one error. And then a state that's closely related to that lives in this complex vector space. So my goal in the rest of the talk is to briefly, obviously, explain where these ingredients arise in this particular K3 sigma model of GTVW. So I need to take a drink of water, and maybe it's a good time to just ask if there are any questions before I move on to the next part of the talk. Okay. So now we need to talk about this particular K3 superconformal field theory. Its main ingredient is that it is constructed out of 6 copies of affine SU2 at level 1. And there are 2 highest weight representations of level 1 SU2 that have conformal weights 0 or a quarter, and where the lowest states are either a singlet or a doublet of the global SU2 part of the affine SU2 symmetry. And the fusion rules of these two highest weight representations are isomorphic to F2. So you can see that we have 6 copies of something that has a kind of Z2 or F2 label. So you start to see some possible connections to the codes. The Hilbert space of this conformal field theory can be decomposed into holomorphic and anti-holomorphic parts. We're not doing holomorphic VOAs, but rather conformal field theories with both holomorphic and anti-holomorphic parts. And these labels live in a set S, where S and S bar are labeled by elements of F2 to the 6th that label which representations occur, and the components S alpha are the same on the left and right up to a universal part X, which can either be 0 or 1. This gives you a spectrum that is not completely local. It's rather non-local by the fact that it includes half integer dimension fields, which you need in order to define the superconformal generators. So this model has n equals 4 superconformal symmetry. And there are presentations of it that make this obvious. So for example, it has a presentation where you start with a 4-dimensional torus at the enhanced symmetry point in string theory, where it gives you affine D4 at level 1. And then you do a Z2 orbifold of that. So it's a kind of special Kummer surface construction. And that is well known to have n equals 4 superconformal symmetry. But in the presentation I've given in terms of 6 copies of affine SU2 at level 1, it's far from obvious that it has n equals 4 superconformal symmetry. So in particular, it has 4 holomorphic dimension 3/2 0 fields, and it has 4 anti-holomorphic dimension 0 3/2 fields. And what I want to explain is that the construction in this language of the superconformal symmetry of this model proceeds via quantum error correction. So to do that, let's note that each SU2 factor has 2 dimension 1/4 primaries, the 2 primaries that create the 2 states in a doublet of SU2. And therefore, you can make a holomorphic dimension 3/2 field by taking a product of 6 of these labeled by a plus or minus 1, where the plus or minus 1 is labeling which of the 2 dimension 1/4 fields you're talking about. So in other words, there are 2 to the 6th possible dimension 3/2 fields.
Sorry, quick question. Is it possible to say where these 6 SU2s are in that D4 presentation?
Sort of, if I can recall. So D4 is SO8, which contains SO4 times SO4, which contains, which is the same as SU2 to the 4th. But this is a super version of D4. There are also fermion fields, and the fermion fields, I believe, to give you another SO4, and I think so altogether you get SU2 to the 6th from doing this kind of decomposition. Maybe one of GTVW, if they're in the audience, can correct me if I just said something wrong, but I think that's how it works. So this means that we can associate a dimension 3/2 operator to a state in the 6-qubit Hilbert space. Or if we're given a state in this space, which is some linear combination, we can associate to that a dimension 3/2 operator. So now what we're going to do is we're going to translate properties that we want our dimension 3/2 operator to have into properties of the state viewed as a state in the 6-qubit Hilbert space. So the main property that we have to demand of this operator is that it gives rise to the n=4 superconformal algebra involving SU2 currents and the stress energy tensor. So that is encoded in the OPE, and so the OPE of two of these operators of dimension 3/2, well, I'm actually doing the same one because we're just going to focus on that for the moment. This takes the form S bar S over Z12 cubed plus a term that involves S bar S over Z12 times the stress energy tensor, plus a term with some constant, which we don't care about, which involves S bar sigma ABS JAJB over Z12. And here sigma A is a kind of multi-label for the ith Pauli matrix occurring in the alpha slot. And sigma AB is the usual commutator. Now, this term is not supposed to appear in the OPE. It's not consistent with even n=1 superconformal symmetry. So we have to require that S bar sigma ABS is equal to 0. But if we translate that back into properties of states in this 6-dimensional complex Hilbert space, this is the quantum error correcting property. It says that the error or it says that distinct errors give orthogonal states. Because this is the inner product of an error associated with the label B with an error acting on a state associated with the label A. So in order to detect and correct the states, this orthogonality property is required, and that is precisely this vanishing condition on this coefficient in the OPE. And in fact, you can write down very explicitly what the state is that corresponds to the different superconformal generators.
Jeff, you have 10 minutes.
Thanks. So the state that corresponds to n equals 1 superconformal generator can be written explicitly as a quarter sum over words in the hexacode times h of w times the state 0 to the 6th. And h of w is something that is defined up here. So in this theory, we have SU2 to the 6th, and SU2 has a subgroup of called the quaternion group, which consists of the identity and then plus or minus I times the 3 Pauli matrices. There is a homomorphism from the quaternion group to the field, well, not the field F4, but rather F4 as an abelian group, which is just Z2 times Z2. And H is a section of this given by the formula here, which tells you how each element of F4 plus maps to an element of the quaternion group. So you take that element here for each, well, you extend it to F4 to the 6th in the obvious way, and then you act on the state 0 to the 6th, and that is the state that corresponds to an n equals 1 superconformal symmetry. And it's non-trivial that this state is a unitary operator times this maximally entangled state that I talked about earlier in quantum error correction. And we thank Tom Maniero for a computation that determined explicitly that this was true and found the unitary operator. So the upshot of this is that, well, first of all, you can extend it to n equals 4, slightly more complicated versions, but still involving properties of quantum error correction, give you all 4. But if you just pick one, then there's a very beautiful connection between the properties of this n equals 1 superconformal generator and this special state that occurs in the theory of quantum error correction. There are a number of other things in our paper. I guess I'll try to mention one of them briefly, but then I'll definitely be out of time. I guess one thing I should mention before I'm completely out of time is that one can ask whether this kind of connection between superconformal symmetry and quantum error correction extends to other models. And we do an analysis for the theory that has moonshine for the Conway group that John Duncan has investigated and show that it's true there. And there's an interesting list of holomorphic VOAs that Theo Johnson Freyd has investigated. And it would be interesting to look there. So the final thing
excuse me, Jeff?
Yes.
Yeah. When you make this statement about the unitary operator, I assume you're saying something special about the unitary operator. Otherwise, this seems to be a, why does this statement have some content?
It's a local unitary operator. It's a product of unitary operators at each of the 6 factors.
Ah, okay, so I see.
Yeah. I guess I was assuming that. But yeah, so I mean, it preserves the maximal entanglement of the state.
I see. Okay, thanks.
Jeff, you skipped over the pink lemmas. Was that intentional?
I can't really hear you, Greg.
You skipped over the pink lemmas. Was that intentional?
I only have so much time.
Okay, but there. Okay.
Yeah, I'm skipping over a lot of things. Anyway, yeah. So let me just mention one last thing, because I started out in the motivation saying that M24 is the automorphism group of the Golay code. So it seems like if we could understand the Golay code, we ought to be able to understand Matthew Moonshine. And we failed, but we failed in an interesting way. And maybe the interesting way that we failed will suggest something to someone else. So there is the six copies of the quaternion group that we get by embedding quaternion group into SU2. And let's consider an n equals 1 holomorphic superconformal generator of dimension 3 has 0, and an anti-holomorphic one of dimension 0, 3/2. So in other words, we're going to look at 1-1 superconformal symmetry. And then we're further going to look at a parity transformation that interchanges the SU2s on the left and right and interchanges psi left and psi right. And although I'm not going to give you the details, you can extend the quaternion group to include this parity transformation. And you can ask what the stabilizer is in this extension of the quaternion group of an n equals 1 supercharge, which is psi left minus psi right. So that defines a certain group. This group acts on the space of Ramon ground states of this sigma model. And the space of Ramon ground states in this model is the space of dimension 1/4 operators, and it's just a 24-dimensional space, which is a 2, under SU2 left times SU2 right, labeled by the 6 SU2 elements. So this you can think of as very similar to the MOG, where the 24 ground states are labeled by a row and a column, where the column tells you which SU2 and the row tells you which one of the 4 states. So there is a representation that you get of this group that stabilizes an n equals 1 non-chiral superconformal symmetry within this extension of the quaternion group. And this is the Golay code. So we found M24 in the GTVW K3 sigma model. It's the automorphism group of the representation of this stabilizer group that you get acting on the Ramon ground states. And when we first discovered this, we were running around Aspen, jumping up and down with joy, because we figured if we found the Golay code, we had to have explained M24 moonshine. But a couple days later, we were walking around with despair because we couldn't see how to connect this Golay code to the way that it occurs in Matthew moonshine, where it acts on the n equals 4 superconformal decomposition of the elliptic genus. And this doesn't seem to, this is a symmetry group it's an automorphism group of a symmetry group. And we were not able to see a connection between the M24, that's the automorphism group of the group defined this way, and the Matthew moonshine phenomenon. But maybe someone in this audience is smarter than we are, and we'll figure out that there is some connection. But in any event, there are a number of other things that we did in our paper, which I haven't talked about and I think are interesting. I've tried to focus on a couple of elements. It's an incredibly rich, intricate theory with really cool connections to both classical codes and quantum error correcting codes. And there's perhaps more to the story, but that's all I know for now and all I have time for. So I'll stop.
Thanks a lot, Greg, Jeff, for that beautiful talk. So let's Applause. Yeah, so we are right on time. So I would suggest that we postpone questions for Jeff until the discussion session. Now, I remind you that Jeff will not be there for the first part, and then at some point he will pop in and probably also be present tomorrow, right? If you want to ask.
Yeah, I'd be happy to, yeah, like the last 20 minutes today and in the discussion section tomorrow, I'd be happy to answer questions.
Okay, perfect. Thank you very much.